Good morning, afternoon, or evening. My name is Jordan, and today we'll be talking about oscillations, or more specifically, spring oscillations. As always, we'll first start with the fundamental principle, and that's the momentum principle, which states that the net force is equal to the derivative of momentum with respect to time. Of course, we've been able to rearrange this equation numerous times to get that force is equal to mass times acceleration. But, as always, it's a key principle, so I have to bring it in. Next, we're going to go over Hooke's law and the vector spring force. We start with Hooke's law, which states that the force of a spring is equal to negative k delta x. A bit of work put into vector form and changing delta x to s yields us the vector spring force, which states that the force of spring is equal to negative ksl, where s is equal to the magnitude of L minus L naught. Right here is our video where we'll be grabbing all of our data and making our computational model to compare to. Now, information we were able to gather from Tracker is that the mass of the spring is equal to 0.402 kilograms, and the average period of oscillation is 1.6334 seconds. We still need to find the spring stiffness and the relaxed length. Finding the spring stiffness can be a bit tedious, but it's okay. We're able to find it. We're able to first find that T is equal to 2 pi square root of m over k. We can solve for k by rearranging the equation, and we were able to find that k is equal to 5.9484 newtons per meters. Find the relaxed length of the spring was a similar process to us finding the stiffness. We were able to find that L naught is equal to 0.0377 meters by rearranging the vector spring force equation. Now, here's our VPython code, where we'll actually bring all of that stuff we just talked about into play. Of course, the gravitational constant is equal to 9.8 meters per second squared. I just imported our k sub s, our L naught, our L, our L hat, and our s. Now we have to bring in the vector forms of all the equations into play, where we're able to find the gravitational force, the spring force, the sum of the two equaling the net force, and now we're applying the momentum principle to update velocity and position, where the ball's final velocity is equal to its initial velocity plus acceleration times time, where in this case acceleration is equal to net force divided by mass, and the ball's final position is equal to its initial position plus velocity times time. We're also able to update the spring stuff with L, L hat, S, and the axis. Now, introducing our second fundamental principle, the energy principle, which states that the change in energy done by the system is equal to the work done by the surroundings plus Q. Q is usually reserved for stuff like heat, but we don't have to worry about that for our matter. In our case, the change in the energy done by the system is equal to the change in potential energy done by gravity, plus the change in potential energy done by the spring, plus the change in kinetic energy. The change in kinetic energy we know is always 1/2 mvf squared minus 1/2 mvi squared. Using the energy principle, or first law of thermodynamics, we're not able to implement this entire VPython code, as you can see down below. In this snippet of code, we're finally defining what delta K, delta UG, delta US, and delta E are, which respectively are the change in kinetic energy, the change in gravitational potential energy on Earth, the change of spring potential energy, and the change of the total energy. Now here's the video showing our computational model in comparison with our experiment model. As you might notice, the y-axis is a bit off, but I will go into more detail about why is it off somewhat. Was the energy principle satisfied? We can now ask why was our y-axis somewhat off from the original. In real life, there could have been a variety of other factors going into play, such as thermal energy, rotational kinetic energy, vibrational kinetic energy, a bunch of other things that might have affected our y-axis results from not perfectly matching our real-world model. Regardless, we weren't able to prove from the graph in the video at the top that the energy principle was satisfied. And now, I just want to say thank you for watching, being throughout this whole journey with us, and stay tuned for Lab 5. See ya.